Hi everyone, and welcome to this presentation on the IDEA project. I will give you a short overview of the IDEA project and give the main results of our work on the preservation of algae. IDEA stands for the implementation and development of an economically viable algae-based value chain in Northwest Europe. It is an Interreg project in which 8 different research partners are involved. From the Belgian side we have VITO, Innovatiesteunpunt and Thomas More Kempe. We have Centraal Supélec from France, VIT Design Lab and the University of Twente from Holland. Productcentrum Jülich is our German research partner, and from Ireland we have the Irish Agricultural and Food Development Authority. VITO is a leading partner in this project. So in the IDEA project, we aim to study the whole algae value chain. We look at the strain selection, where it is important that we select strains that grow well in the Northwest Europe region and that allow a year-round production. We look into algae growth, algae harvesting. We look into the preservation and the logistic aspects that come into play. These are things that are often forgotten. And finally, we also look into the processing of algae into final end products. At VITO, we mainly work on the harvest of algae, their preservation and the final processing. For the harvest, we focus on the use of membrane technology, and this will be explained further in another presentation that is given by Leen Bastiaens in this conference. For this presentation, I will focus on the preservation work that we did at VITO. Why is preservation needed? Well, in practice, it is often very difficult to organize processing immediately after the harvest. The moment on which the algae need to be harvested is partially unpredictable because algae growth depends on the weather conditions. Moreover, we prefer to organize the algae growth and its processing on different locations. So we aim to develop an economically viable value chain, and therefore we prefer to have the processing on one central spot. When the algae are cultivated on many different locations and then collected and brought to one central place, the equipment for the processing can be shared among the different algae cultivators, and the processing costs can be reduced. However, when we want to organize it in this way, we need to preserve the algae for some time. So algae preservation is needed. So we want to store algae in between their cultivation and later processing. And for this intermediate storage, we prefer to store them in a wet way, so without a drying step. In this way, we avoid drying costs and we have no loss of heat-sensitive nutrients, something that is often seen when heating is used for the drying step. Moreover, we have a minimal loss of algae viability when they are stored in the wet way. And this minimal loss of algae viability is important when aquaculture and applications are envisioned. We did preservation tests on a lab scale, and I will show you the results immediately. And at the moment, we are still working on pilot scale preservation tests. And on the picture on the slide, you can see the storage tanks that are currently used for those pilot scale tests. So first, we studied the preservation of Nannochloropsis galitana. We used concentrated paste that were stored at 3 different temperatures in plastic tubes that were closed either by a plastic cover or by a cotton plug. So in the latter situation, we still had some air exchange with the environment. And for one storage condition, we also tested the effect of adding acetic acid. So we saw many changes during the preservation of Nannochloropsis, but one of the main things was a fast decrease in oxygen levels. So you see here in the left top corner the graph that shows the oxygen levels for the algae that were stored in a closed tube. And then you see that already after a couple of days, the majority of the oxygen is gone. This has, of course, a strong impact on the total number of bacteria and then especially on the aerobic count. And that is what you see in the right top graph. This shows the total number of microorganisms for all storage conditions and then grouped by storage time. And then you see a clear decrease for all storage conditions in function of time. In addition, we noticed that when algae were stored under inappropriate conditions, that a lot of bad smells were formed. We studied the headspace of the algae stored in closed tubes and noticed the formation of hydrogen sulfide, but also the formation of organic sulfur compounds with a bad odor next to the formation of volatile organic compounds that are known to cause bad odors. Luckily, we were able to reduce the formation of these smelly volatile compounds. This could be done either by cooling the algae or by storing them in an open tube that was shaken. So by storing them in this way, we could have air exchange with the environment, and this had a positive effect on the formation of these bad smells. Also, the addition of acetic acid had a positive effect on the formation of these smelly compounds. Moreover, it also had a positive effect on the total number of microorganisms in the samples after storage, and it also reduced the number of yeast and molds. However, when acetic acid was added and the sample was stored for more than 7 days, we also saw some negative effects. Lipids were hydrolyzed and chlorophyll could be degraded. So from these results, we can conclude that for an optimal Nannochloropsis preservation, we should cool the algae and we should have an air exchange with the environment as much as possible. And the addition of organic acid can help and can improve the preservation, but the dose of acid that's being added needs to be adapted based on the storage time and the end application that is envisioned. Now I want to show you our results on the work on the storage of Porphyridium. Porphyridium was stored in the lab in 2 different ways, either as a concentrate or as a dilute culture, and the storage was done at 3 different temperatures, 4, 8 and 20 degrees. There was a tendency for higher microbial numbers after concentrate storage than after dilute culture storage. In addition, there were clearly higher levels of smelly compounds after concentrate storage than after dilute culture storage. But the main issue with the concentrate storage was the formation of a strong gel network and a very fast and strong viscosity increase when Porphyridium was stored as a concentrate. Already after 1 day, but probably even already after a couple of hours, we saw a very strong increase in the viscosity, as you can see here on the bottom left graph, especially at 20 degrees. In addition, we also saw a strong formation of a gel network. We saw a significant loss of organic matter during concentrate storage, and this already after 1 day. This organic matter loss was stronger for 20 degrees storage than for the cooled storage, and was related to a loss of carbohydrates, especially glucose. And it can probably be explained by degradation of Floridian starch and respiration losses. From these data, we can conclude that Porphyridium should be stored as a dilute culture and not as a concentrate. This brings me to the end of the presentation. Thank you very much for listening, and please visit the IDEA website to find more information on our project.